throughout our history, we have managed to stay a leader in the technology necessary to design and manufacture components for the automotive aftermarket industry. We are proud of our record in supplying this market and the mechanic in particular with quality parts, components, and materials necessary to stay proficient and profitable in his workplace. As you well know, it is not an easy task to stay current with the latest changes in automotive technology. I'm sure you're very much aware of the information explosion. In the middle 60s, the mechanic could get by reading 5,000 or 6,000 pages of new text every year and still remain proficient. Today, the very same mechanic may have to master over 500,000 pages of text. Astounding! But by using the same technology that made these changes in the automotive industry possible, electronics and computers, we can also help minimize the effects of the information explosion.
The Corporate Training Department of Standard Motor Products continues its corporate mandate to supply our customers with the knowledge necessary to stay on top of the changes of the automotive industry. During this video training program, we will supply you with the information to understand and repair the Kelsy Hayes 4-wall system, the Bendix and Delco Moraine of anti-lock brake systems. Hello. Our discussion today is about brakes, anti-lock brakes in particular. Now, while other systems in the automobile have changed over the years, it's only been recently that the brakes on an automobile have changed. Let's take a look. It wasn't that many years ago that you were familiar with a single master cylinder, 4 drum brakes, and manual adjusters. Today, anti-lock brakes are found on over 50 models and brands of automobiles and trucks. As each day passes, more and more vehicles are equipped with anti-lock brakes as standard equipment. In fact, over the last 3 or 4 years, we've gone from almost no anti-lock systems at all to as many as 5 major manufacturers. There's Bosch, Tevez, Kelsy Hayes, Bendix, and Delco Moraine, and there are still others used overseas. The driver and the mechanic should keep some very important facts in mind when working on or trying to troubleshoot a vehicle with anti-lock brakes. The system is there to provide the driver with the means to better control the vehicle. With better control and better traction, shorter stopping distances will result. But it is extremely important to be aware of the fact that anti-lock brakes are not anti-skid. They're not a miracle device. Anti-lock brakes, for example, will not stop a car that has hydroplaned because of excessive speed when traveling in wet weather. Anti-lock brakes may not provide the optimum braking in powdery snow, and they may not stop a vehicle that is already in a sideways slide. Since this program deals with 3 different types of systems, we will cover each one separately. But even though they are different, they share certain common operating principles. Kelsy Hayes, Bendix, Tevez, Bosch, Delco Moraine all operate on the common principle of counting the rotation of the vehicle's wheels and then supplying the information to a microprocessor. The processor, or computer, compares the incoming information to pre-programmed memory, makes a calculation, then outputs a signal to control the hydraulic pressure to a locking wheel. The component or signaling device that feeds the computer information about a wheel's rotational speed can be referred to by many different names, including shutter, tone wheel, R-wall sensor, axle sensor, speed sensor, deceleration sensor, etc. But they all operate on the very simple principle of electromagnetism. The wheel speed sensor is made up of permanent magnetic around which is wrapped a coil of wire. A shutter wheel or armature is passed through the magnetic field. The magnetic lines of flux are broken by passing the teeth of the wheel through the magnetic field. This induces a voltage in the coil of wire which relates directly to wheel speed. Since the gap between the sensor and the rotating tone wheel is critical, the gap should always be checked as part of any of the replacement procedure. If the air gap is too large, a signal will not be generated to the computer. Another component that is common to all anti-lock systems is a computer or microprocessor. These can be referred to as an ECU, Electronic Control Unit, EBCU, Electronic Brake Control Unit, EHCU, Electro-Hydraulic Control Unit, EBCM, Electronic Brake Control Module. But they all basically do the same task. Each acts to control braking pressure in an attempt to prevent wheel lockup. The ABS computer receives sensor input readings from each of the wheel speed sensors. Some systems use one sensor, other systems may use up to 4 sensors. The computer also receives signals from the stop light switch and power from the ignition circuit. On integral systems, it also receives inputs from pressure monitoring switches for the power booster unit. The computer compares the various inputs to pre-programmed memory. It then performs calculations and outputs controlling voltage signals, or it completes ground circuits for hydraulic modulator pressure control solenoids. The computer also uses its self-test results and diagnostic programs to turn on warning lights if the system malfunctions. It is important to understand that most anti-lock brake systems actually contain 2 microprocessors. Each one checks the other, as well as receiving the same input signals for comparison. If either computer malfunctions or if their outputs disagree, the system will not operate in anti-lock, but instead the vehicle will retain normal braking function. Each time the ignition key is turned on, power is supplied to the microprocessors and the electronic solenoid, and if equipped, the hydraulic brake booster. The computer cycles the system through a self-test function, checking each of its electronic components. If the system passes the test, the dashboard indicator lights will turn off, telling the operator that the system is functioning properly. If a malfunction is detected, individual anti-lock or brake lights will remain illuminated, alerting the driver of the failure, and the system will stay in normal braking mode. All anti-lock systems operate in 3 modes. First, the pressure application mode. This obviously refers to brake pressure application. The second mode is hold or isolate. Here, the computer isolates the master cylinder output pressure from a locked wheel. Operation in the third mode is referred to as dump, reduce, or release. All 3 refer to dropping or lowering the pressure at the locking wheel. Remember that these cycles can be repeated 10 to 15 times a second if needed to retain wheel traction. Now, let's review an anti-lock cycle common to all electronically controlled systems, regardless of the differences in their hardware. With the application of the brake pedal pressure, the master cylinder's pistons increase hydraulic pressure to the calipers and/or wheel cylinders. Regardless of the system design or the type of device utilized to modulate hydraulic pressure, the modulation devices are open to hydraulic pressure. As the vehicle begins to decelerate, the wheel speed sensors will detect the likelihood that any given wheel or axle is losing traction. If needed, the computer will supply power to the windings of the modulating devices or solenoids. As the valves activate, they will stop the increase of hydraulic pressure to any wheel that is locking. This is called the maintain or hold mode. The computer continues to monitor wheel speed. It determines that the wheel is continuing to lose traction. The computer signals the system to reduce or bleed off pressure from the locked wheel, while preventing any additive pressure from the master cylinder from entering the system. The wheel pressure will be bled or dumped to a hydraulic accumulator or storage device, and the system will cycle again. In fact, the entire cycle can repeat at a rate of 10 to 20 times per second, opening and closing the solenoid valves as needed to maintain traction. Now, let's take a closer look at the Kelsy Hayes 4-wall system. Remembering the 4-wall system is primarily used by General Motors Corporation on the 1990 M Series and 4-wheel drive L Series, also in the 1991 S and T Series 4-door vehicles. This system is a non-integral anti-lock braking system. It has a traditional step-bore master cylinder and vacuum brake booster. Unlike the early RABS and R-wall systems, this system works with all 4 wheels. An electronic controller, referred to as an EHCU, Electro-Hydraulic Control Unit, is the controlling center. It can be found located adjacent to or under the master cylinder. The EHCU consists of the electronic control unit, or ECU, the hydraulic control assembly, a pump motor for the accumulator unit, along with relays and control circuits. An illustration of this system's electrical circuits shows that the vehicle utilizes four-wheel speed sensors at left front, left rear, and right rear. The instrument panel in the vehicle has a red brake light circuit, an amber anti-lock circuit, and a four-wheel drive light on vehicles so equipped. Diagnostics for the vehicle are accessed through the ALDL connector, the same connector that is utilized for the electronic ignition testing. The EHCU performs a self-test, circuit check, and an external test of continuity in the wheel speed sensors, stoplight switch, etc. As the vehicle begins to move, it also performs an electro-hydraulic functional check of the pumps, solenoids, and other devices. When a speed of 8 to 10 miles per hour is achieved, the ECU will enable the anti-lock system. It is important to note that if a driver brakes with his left foot and never releases the brake pedal, that the anti-lock circuit will not activate. You can see that the electro-hydraulic control unit is a fairly compact device. It contains an electric motor to drive the accumulator pump, one front and one rear low-pressure accumulator, a front and rear high-pressure accumulator, and also a front and rear bleeder screw, which must be utilized when servicing the system. The hydraulic circuit is laid out to route fluid pressure from the primary and secondary chambers of the master cylinder through a traditional combination valve, which contains a metering valve, proportioning valve, and pressure differential valve, then through the electro-hydraulic unit. The hydraulic circuits supply pressure to the right front and left front separately, and to the rear as another separate circuit. To complete a look at the Kelsy Hayes four-wall system, follow along as we go through one complete cycle of the electronic hydraulic control unit. During normal braking, fluid pressure from the master cylinder moves through the ISO isolation valve. It is de-energized or open. The PWM pulse width modulation valve is also open, allowing fluid from the ISO valve to move from the master cylinder to the appropriate wheel. Each low-pressure and high-pressure accumulator circuit is void of pressure. The brake system is in normal mode. As the vehicle begins to slow, the wheel speed sensors will signal wheel speed rotation. Suppose that during braking, the rear wheels begin to lose traction. The ECU senses the loss by measuring deceleration rate of the wheels. The ECU stops fluid pressure from the master cylinder by energizing the ISO valve. The PWM valve remains de-energized. If the wheel does not gain rotational speed within a predetermined period of time, the ECU will energize the PWM valve to reduce wheel cylinder pressure. The released pressure will charge both the low-pressure accumulator and the high-pressure accumulator. Simultaneously, the computer will energize the electric motor, which turns the two-channel pump. As wheel speed rotation is regained because of a reduction in pressure, the ECU will open the PWM valve while still maintaining closed the isolation valve. Pressure from the front channel pump, high-pressure accumulator, and low-pressure accumulator will now tend to stabilize, allowing the brakes to reapply. If the wheel continues to hold traction, the next step is for the computer to open the ISO valve to allow master cylinder pressure to again apply the brakes. Now that we've covered system operation, let's discuss diagnostics. Two dashboard lights are used to signal the operator of any system problems: the red brake light and the amber anti-lock light. The amber light also displays trouble codes on some systems. When a brake or anti-lock light is illuminated while operating the vehicle, it indicates a problem. But don't ever assume that it's an electronic problem. You should first eliminate the normal problems that are brake-related. Check the fluid level in the reservoir. Check the brake shoes and pads. Then do a visual check of electrical connection, fuses, stoplight operation, and sensor connection. Also check for mud or dirt buildup at the sensor. Then you may test the system with the onboard test system. Testing a GM four-wall is easily accomplished by connecting pins A to H at the ALDL plug, then turning on the ignition switch. Watch the amber anti-lock light. The first codes will be a 1, 2 on a two-wheel drive vehicle or a 1, 4 on a four-wheel drive vehicle. Each code will flash 3 times. These will be followed by any stored codes that are in memory. Each stored trouble code consists of 2 digits. Though many diagnostic codes can be delivered by the computer, most problems are related to items which are easily checked with an ohm meter or voltmeter. One item easily checked is the wheel speed sensors. Check resistance and the output signal of the wheel sensors. You can perform a simple test by first disconnecting the sensor's lead at the nearest connection point. Set your meter to a low resistance scale. You're checking for continuity. The exact resistance specifications are available in specific service literature. Another quick test that can be done is to switch the meter to a low voltage AC scale. Connect the leads across the sensor terminal, then rotate the wheel. You're looking for a voltage reading. It will increase with an increase in speed. If the resistance is good but a voltage signal is not present, check the air gap. After repair, the technician should always clear the trouble codes from memory. This is done by turning the ignition switch to the run position, installing the jumper between terminal A and H, waiting 2 seconds, and removing the jumper wire for 2 seconds. Then repeat the grounding and ungrounding procedure 2 more times. Next, let's look at the Delco Moraine Anti-Lock Brake System ABS3. The system is used on 89 to 90 Oldsmobile Cutlass Supremes, Buick Regals, and Pontiac Grand Prix. In 1991, additional models were added: Chevy Lumina, Celebrity, Beretta, and others. The system employs 4 individual wheel speed sensors. The hydraulic circuit is routed left front, right front, and both rears as a unit. A 3-channel design. Another interesting feature of this system is that it uses a traditional proportioning valve mounted in the rear of the vehicle. The heart of the ABS3 anti-lock system is the Power Master 3 master cylinder. It has 2 master cylinder pistons. The primary supplies pressure to the right front. The secondary piston supplies pressure to the left front. The power brake booster pressure chamber supplies pressure to the rear brakes. The booster segment of the master cylinder consists of an electrically driven pump that utilizes brake fluid to pressurize an accumulator and the booster assembly, which powers a 3rd piston in the master cylinder. The booster is designed to operate at pressure as high as 3,400 pounds per square inch. The operating or controlling solenoids are plugged into the top of the master cylinder casting. The fluid reservoir for the brake fluid is then mounted on top of the solenoids. Servicing any portion of the hydraulic system should only be done after bleeding down the accumulator pressure. This is done by turning off the ignition key and pumping the brake pedal 30 to 40 times. The Delco anti-lock system also has a self-test function, which will illuminate the red or amber lights on the dashboard when a failure is detected. The system can also store diagnostic codes, but unlike some other systems, diagnostic codes cannot be read out unless you have a scan tool with the proper test programs. The last system that we would like to familiarize you with during this anti-lock video segment is the Bendix anti-lock system. The Bendix system is available on 1989 and 1990 Jeep Cherokee and Wagoneer models. The Bendix anti-lock system is an integral system. It provides for 4-wheel anti-lock using the select low principle. It uses an electrically driven pump to supply hydraulic boost instead of a vacuum booster. Notice where the booster pump assembly is mounted. In the Jeep, it's found on the right fender apron. It connects to the master cylinder with 2 hoses, a low pressure and a high pressure hose. The power booster supplies pressure to the master cylinder for power brake operation only. The front piston in the master cylinder supplies pressure to the front wheels. The rear piston of the master cylinder supplies pressure to the rear wheels. a typical tandem split hydraulic system. The system even utilizes a pressure differential valve similar to non-anti-lock vehicles. The output of the master cylinder's booster section supplies boost to the master cylinder's pistons and also supplies high pressure to the pressure modulator assembly. Interconnected between the power booster output and the rear brake line on the master cylinder is a boost pressure differential switch. The function of the boost pressure differential switch is to monitor the pressure difference between hydraulic booster pressure and the master cylinder's primary piston pressure. The switch is actually built into the hydraulic modulator assembly. The unit is designed to alert the driver of a failure in the booster circuit when master cylinder pressure can exceed booster pressure if a failure were to result. This system also utilizes two accumulators. One accumulator is located inside the booster pump assembly, along with the pump motor. The second accumulator is located next to the master cylinder and power booster unit. Both of the accumulators can store approximately 2,000 pounds per square inch pressure to assist in power brake operation and fluid cycling during anti-lock mode. Let's go through a complete cycle of operation of the Bendix anti-lock system and show you how it works. Once a vehicle is moving, the system becomes activated. As the driver applies brake pedal pressure, it is applied by the master cylinder in conjunction with the power booster through the modulator to each of the wheel assemblies. The isolation valve solenoids are normally open to the pressure of the master cylinder. The wheel speed sensors supply the computer a rotational speed signal from each wheel. The computer monitors these speed readings and utilizes the highest speed for a vehicle deceleration baseline. Each of the remaining wheel speed sensors' output must be within a certain percentage of the baseline as the brakes slow the vehicle. The computer, through its pre-programmed memory, will determine which wheel is decelerating too rapidly or whose rotational speed is decreasing too quickly. On sensing that a wheel is about to lock, the computer supplies a signal to the isolation relay for a particular wheel. When the isolation solenoid is activated, it closes, effectively isolating the master cylinder and booster from increasing pressure at the locking wheel. If the wheel does not gain rotational speed, the computer will then open the decay or dump solenoid, effectively reducing the pressure at the wheel that has locked. The computer will continue to monitor rotational speed, and as speed picks up, the computer will allow the build solenoid to open, controlling pressure on and off to the brakes during anti-lock operation. The pressure that is applied to the brake during anti-lock operation at this point will be pressure from the accumulator and the booster section of the pressure modulator. You should be aware of certain inherent faults which may present themselves in the Jeep system. First, if the operator were to operate this vehicle over 4 miles an hour with its parking brake applied, a fault code would be indicated by having both the red and amber lights illuminated. Obviously, if the parking brake switch were to stick closed, the same indications would be present. Another point to remember is that a low fluid level in the reservoir will cause the red warning light to illuminate. This will happen when the pads wear low or if a leak were to develop. Since these vehicles will undoubtedly be used off-road, any sudden deceleration of a wheel while in four-wheel drive low may cause the red brake light to come on momentarily and then go out. The system is okay and no fault or problem exists. The system does have built-in self-diagnostic capability, but at the time of this writing, it will be necessary to use Chrysler's DR-B2 scan tool to retrieve trouble codes. But remember, always check the obvious first: fluid level, wheel sensor resistance, and signal output, and a good visual inspection. Well, that's a brief look at the new anti-lock systems. In future programs, we will concentrate on studying diagnostics and repair for each anti-lock system separately. Additional information on anti-lock systems is available on other tapes in the brake series, including Kelsy Hayes Arwall, Tevez, Bosch 2, and Bosch 3. I'd like to take this opportunity to thank you on behalf of the Corporate Training Department and the ICE Division of Standard Motor Products for your support of our product line.
vehicle begins to slow. The wheel speed sensor's output allows the computer to make a decision about the slowing of each particular wheel. Suppose that a wheel is about to lock. The computer signals the sensor block to control the ground for that wheel solenoid valve. It moves the valve to a hold pressure position. Since the operator is still applying the brake pedal with the same amount of force as originally applied, the solenoid valves will hold additional pressure from being applied to that wheel. If the wheel continues to slow too rapidly after a predetermined period of time, the computer will increase the current flow through the solenoid's coil and move the piston to a third position. In this position, the fluid pressure to the wheel would be reduced or released. Once the sensor senses wheel rotation, it would allow the brake fluid pressure from the master cylinder to be reapplied to the particular wheel. During the time that anti-lock brake application is taking place, the released pressure would travel back to the master cylinder reservoir and/or simultaneously enter the replenishing valve. During this sequence, the operator does not feel or see any changes in pedal height. During the release of brake pressure in the anti-lock function, or when under extremely hard braking without anti-lock, pedal height is held in place by the replenishing circuit. The replenishing valve serves to maintain that height by redirecting a portion of the released or recycled accumulator pressure through a relief valve back against the master cylinder pistons. The replenishing function is similar to the accumulator function in the Bosch 2 system. The sensation of driving a car with Bosch 3 brakes is that of a hard pedal. You actually don't feel any pedal pulsation similar to the Bosch 2 system. Now that we understand the function, components, and interaction of the two Bosch systems, let's take a closer look at servicing the vehicles. One of the first service problems that a mechanic will be confronted with, other than a diagnostic light on the dashboard, will be simply doing a brake job. As you can see on this Volvo with a Bosch 2 system and anti-lock brakes, the calipers are traditional in appearance. If the repair is simply replacing the pads, do as with any other system. There is really no interaction or complications because of the anti-lock system. The only precaution this manufacturer recommends is using good quality brake pads designed for the particular vehicle. Inexpensive or soft pads can cause a problem with the anti-lock braking system. Whenever refinishing the rotor, it is highly recommended that you resurface both rotors across a given axle with the same type of surface finish. Experience has shown us that installing a new rotor on one side and a resurfaced rotor on the other can cause premature shutdown of the anti-lock function, even though braking feels normal. With the repairs completed on a Bosch 2 system, your next concern is bleeding the air from the system. Since this is a non-integral system, a pressure bleeder is the best method of removing air from the hydraulic circuit, including the wheel solenoid valve modulator assembly. Pressurize the system in a traditional manner using the appropriate master cylinder adapter and alternately open the bleeder screws to remove the air. Always consult the manufacturer for specific recommendations on bleeder opening sequence. The next service problem that a mechanic will be confronted with in an anti-lock system is a failure indication by the illumination of either the orange anti-lock light or the red anti-lock light on the dashboard. Though it is not the easiest way, it is permissible to test the entire anti-lock system using a high-impedance analog or digital volt-ohm meter and doing pinpoint tests, wire tests, and component tests throughout the system. But the original equipment manufacturers and certain aftermarket manufacturers like Autoforce manufactured test equipment and breakout boxes. This system does not have an onboard diagnostic display. It is a simple system to test. With the power off, disconnect the computer multi-pin connector. Connect the test box in its place. Follow the manufacturer's test sequence to pinpoint the problem. Remember, the first indication of a failure in the system will be the constant illumination of the anti-lock light. It is recommended procedure to first check all the fuses and fusible links for power to the various components. Next, without the aid of a breakout or test box, the first test that we would perform would be to check each individual wheel speed sensor operation. Since they are located in a vulnerable place, exposed to the elements of road hazards, they are the most likely component to malfunction. It is a simple matter to test the components using an ohm meter. Check the resistance of the various sensors and the lead wires at each wheel. Manufacturer's resistance specifications are available in various service manuals. Another simple test that can be performed is to set the voltmeter on AC volts and rotate the wheels. A voltage signal should be present and proportional to the rotational speed of the wheels. When working on the hydraulic system of the Bosch 3 system, remember it is an integral system. It has a brake fluid hydraulic booster. To avoid serious injury to either yourself or the system, whenever working on the hydraulics, discharge the accumulator. First, turn the ignition key off or disconnect the power to the system. Depress the brake pedal 20 to 25 times until the brake pedal has become hard. With pressure depleted, you may perform any service function on the hydraulic system. If repair work has been done on the booster system, it must be bled free of air. Fill the master cylinder reservoir to the full level. First, bleed the hydraulic pump and accumulator assembly. This is easily accomplished by installing a hose on the bleeder screw on the right front of the master cylinder and inserting the end of the hose into a jar or suitable plastic container. Turn on the ignition switch. When the pump has stopped, open the bleeder screw. The pump motor will run, discharging any air and fluid into the chamber. As the air is depleted and pure fluid exits the master cylinder, close the bleeder screw and turn off the ignition switch. If you have worked on the hydraulic system, you will need to remove the air from the lines and calipers. You should use a pressure bleeder, though a manual method is acceptable, but very slow. First, fully depressurize the accumulator assembly to avoid personal injury. Remove the electrical connector from the fluid level sensor in the reservoir cap. Install a pressure bleeder adapter onto the reservoir. Charge the bleeder to approximately 20 pounds per square inch. With the ignition key off, turn the pressure bleeder on and bleed each wheel per the manufacturer's suggested sequence. Remove the bleeder assembly. Always extract any excess fluid from the master reservoir until the fluid is at the full mark. Do not leave the master cylinder reservoir over full. Reinstall the fluid warning sensor, connector, and reservoir cap. Turn on the ignition switch and check for proper brake operation. Let's look at diagnostics on this Dodge Dynasty with a fault indication on the dashboard. First, turn on the ignition key to enter self-diagnostics. Make sure that the parking brake is released and fully depress the brake pedal with one hard full stroke and hold. After approximately 5 or 6 seconds, the red brake warning lamp will begin to flash. Note the number of the fault code. If you continue to hold the brake pedal, the sequence will repeat itself until you do remove your foot from the pedal. The system can display 16 fault codes, though only one will be displayed at a time. Also, you should note when the key is turned off, the fault codes will be lost. They are not retained in memory. If you're going to do extensive service diagnostic work on the vehicle, it is advisable to connect a battery charger to maintain the battery. A code 8. This is a signal that a malfunction has taken place in the left rear wheel sensor. If the problem is low output from the sensor when the vehicle is under acceleration, code 8 will not set, but instead code 9. If you do not have a test box, an alternate method can be used to check the sensor. Turn off the ignition switch and disconnect the intermediate sensor connector between the computer and the wheel speed sensor for the left rear wheel. With the car properly supported on a lift, pull the cable out through the bulkhead connector and disconnect the plug. Measure the resistance across the 2 pins. An open circuit. This signifies that the wheel speed sensor must be replaced. You actually are looking for between 800 and 1800 ohms. With the connectors and the unit properly reinstalled, let's recheck it to verify for a proper repair. With the meter set on the voltage scale, turn the wheel. Notice the faster the wheel rotates, the higher the voltage reading. Reconnect the harness and protective clip. Reinstall the harness through the hole in the floor. The onboard diagnostic system in the Chrysler vehicles is merely an indication of the area of the fault. If specific diagnostic work must be performed, it will be necessary to utilize a diagnostic test box. It is a simple matter to connect the box by first turning the ignition key off, then disconnecting the 35-pin connector on the computer located in the trunk. Connect the test box into the system as a substitute for the ABCM computer itself. Since we know we have a fault in the left rear wheel sensor, let's follow the instructions with the test equipment and perform the test function on the left rear wheel sensor. This tester can perform both static and dynamic test functions. With the box connected, turn on the ignition switch. Note that the tester will also do a self-test and light various indicators. Since the indicator for the left rear wheel sensor is not lit, it agrees with our onboard test indication of code 8. The tester can perform numerous operating tests, a switch test of the stoplight switch, S1, S2A, and S2B. It can check the booster pump and motor. It can check the replenishing valve relay and the valve itself. It can also check the hydraulic wheel control solenoid valves. But let's fix the problem. Turn on the ignition key. Watch the indicator as we rotate the wheels. To illustrate, let's rotate each wheel starting at the left front. You can see that the indicator lights as each wheel is rotated, except the left rear. We have just done the same test that we performed with a voltmeter in the manual test method. With repairs complete, you should always road test the vehicle to verify that no other fault codes appear. Always test the vehicle under heavy braking and, if conditions permit, under anti-lock braking. I would like to take this opportunity on behalf of the Corporate Training Department and the ICE Division of Standard Motor Products to thank you for your continued support of our products and sales efforts.